Maybe I should put this first, but nonetheless, let's do it here. So we've been talking about these glacial interglacial cycles and the changes in the time scales and the various time scales and the differences in the northern and southern hemisphere signatures in the observed records from ice cores, sediment cores, and so on. So what are the intrinsic time scales? I already mentioned that tilt has a 41,000 year time scale, but you can see that it's modulated, so it's not a constant. But we know that the Earth's tilt varies from about 22.5 to 24.5, and we are somewhere at 23.45 degrees or so right now. It's the tilt with respect to the plane of the ecliptic on which the planets orbit around the sun, and obviously the tilt determines the seasonal contrast. So when the axis is pointing towards the sun, if the angle is high, you get stronger summer because you're pointing more towards the sun, and the contrast between the hemispheres will be stronger. So the received total amount of energy doesn't change. You just change the distribution seasonally, which is still critical because many of the records show a strong obliquity cycle in the glacial records. And long-term changes in eccentricity, this is Milankovitch cycle, which is mathematically calculable into the future as well. So you can see that eccentricity varies by about 6%. I might have said it wrong before as 2%. Actually, eccentricity variability is about 6%. The resulting radiation variability is, I think, about 0.2%. Okay, but the main point I made is still correct. This forcing is typically not significant enough to start anything by itself, but we will see that eccentricity modulates the precession cycle, and together they produce multiple beats. So the eccentricity cycle has 100,000 year time scale, which we have seen in the Vostok ice cores over the last million years, and then it has a about a 400,000 year time scale that is here again, very uneven distribution. So you can see that if it combines with other orbital parameters, then it can produce multiple time scales, and then you have internal feedbacks which can amplify some intrinsic time scales that we must understand. Okay, so here is the angular motion of the precession. So this is the animation we saw before where the orbit itself keeps wobbling. It's called the precession of the equinoxes or the apsidal precession. So that's going from -1 to 1 as a sine omega, and there is our eccentricity just taken at the 100,000 year time scale, and they together work as epsilon sine w, so you get a modified precessional forcing at 23,000 year time scale that is dominant. So when you actually combine the long-term changes in precession related to the modulation by eccentricity, you end up getting a 100,000 year cycle, 400,000 year cycle, and a 23,000 year cycle. So this begins to tell you how complicated life is, right? Even if radiation forcing is there, like we saw in the case of the glacial cycles, two of the insolation maxima at 65 north showed beginning of deglaciation. The third one didn't do anything. Okay, so many complicated internal feedbacks are involved as well. So if you look again at the cycle amplitudes over these various time scales, so these are individual sine wave time scales. You have 100,000, 41,000, and 23,000, and various combinations can occur, right? So here is 100 plus 100,000 plus 23,000 year cycle combined. Here is the 41,000 plus 23,000 year cycle combined, and here is the 100,000 plus 41 plus 23,000. So you can see the rich spectrum of timescales possible by these forcings, and we have to combine these with the other internal processes that have been invoked, as well as Kepler's laws. For example, as I mentioned before, as the Earth is going around in the orbit, when it is closer to the Sun, it has a catapulting effect, so it moves faster, and when it is far away it moves slower, so the area covered is the same over the same period, which means even if you are closer to the Sun and the summers are hotter, because you are moving faster, the total energy received during the summer can be actually smaller than when you're far away, where the slow movement is going to give you a longer integrated energy. So this could explain part of the shifts from 41,000 year cycle to 100,000 year cycle, but there are also other explanations provided. For example, how the glaciers can slip during melting to lower latitudes and get into higher radiation. So these are kind of let's say hypotheses, but they can be tested with simpler models of land ice and so on. So people like what's his Heuber, is it Bruce Heuber from Harvard, and Elliot Zipperman and various other people work on these issues and produce very nice results. But again, what we are doing is taking time series that have some information and trying to interpret them with all the orbital dynamics and internal feedbacks we know about. The question is, are they relevant for global warming? Not necessarily, but they are critically important for understanding the Earth system as a whole and the feedbacks that are there within them, even though they may not be necessarily relevant. But if there is some kind of a runaway melting of the Greenland ice sheet, moulins going to the bottom, lubricating the ice sheets and sliding them towards the lower latitudes or towards the ocean, lower altitudes, and or the Antarctic region where shelf ice are breaking off in large chunks, and when the shelf ice, which is the extension onto the ocean, breaks off, it affects the dynamics of the glacier that's still on land. It can accelerate the discharge rates, it can slide the glacier and affect the grounding lines, and so on and so forth. So all these dynamics are still important, but the point I would take from this is that the orbital forcing, as predictable as it is, the response to these orbital cycles are not that easily predictable. There are many feedbacks we are yet to understand completely, and the data records are not fine enough to actually allow us to diagnose all these feedbacks just from the data. So we'll need to combine them with models.